Good afternoon to all of you. In today's lecture, we are going to describe the wave mechanics, which is a very important part of the physics syllabus for BTech first year students. So in this lecture, basically, we are going to study about these topics. We will start from black body radiation, and then we will briefly describe this black body radiation problem according to Wien's law, Stefan's law, and then finally Rayleigh-Jean's law. And after that, we are going to describe this problem on the basis of quantum theory, that is the Planck's law of black body radiation. Then we will discuss the wave particle duality, and then we will describe in brief about the wave function. Then we will study the matter waves, and finally we are going to study about the Schrodinger's equations. So basically, before starting, let's first of all understand that what is this wave mechanics and how it is different from the classical physics. Earlier, it was a general assumption of a scientific community that the classical laws of electricity, magnetism, the classical laws of Newtonian mechanics and the laws of heat and thermodynamics, they were able to explain each and every phenomena of nature. But very soon it was realized by the scientific community that these laws were not sufficient to explain each and every phenomena of nature. And one of that very prominent problem of that time was that of black body radiation problem. So if we are having a black body and if it is heated, then the radiation emitted by the black body, how that radiation which is emitted by a black body, that is distributed with respect to the wavelength. That was the problem. So first of all, this black body radiation problem was tackled by Wiens by using his Wiens displacement law. So according to Wiens, Wiens found that the radiative energy per unit wavelength in interval d lambda has a maximum at a certain wavelength lambda m, and at the maximum shifts to a shorter wavelength as the temperature T is increased. So basically he found the law that this product of lambda m, that is the wavelength corresponding that is the maximum wavelength multiply the corresponding temperature, that is always constant. That is lambda m into T, that is equal to B, and B is having a value of 0.2898. So this is what the Wiens law. So on basis of this Wiens displacement law, Wiens basically gave a radiation law, which we will discuss in the coming slides. So this Wiens law was only partially successful in explaining the black body radiation. This Wiens law explained the black body spectrum in the shorter wavelength, but it failed for the longer wavelength. So the search continued, and this problem was again tackled by the Rayleigh-Jeans. So according to Rayleigh-Jeans law of radiation, that gives us the intensity of radiation released by a black body. The law states that the intensity of the radiation emitted by a black body is directly proportional to the temperature and is inversely proportional to the wavelength raised to a fourth power. That is, the energy density given by a black body is equal to 8 pi kT upon lambda to the power 4. So again, this Rayleigh-Jeans law was again partially successful because it resembles the experimental findings in the longer wavelength region, but the shorter wavelength region, it was not properly having an agreement with the experimental findings. So finally, this black body radiation problem was solved by Max Planck by using his quantum hypothesis. According to Max Planck, the energy emitted by a black body is having a continuous distribution, is having a discrete distribution of energy. It is not having a continuous distribution as was assumed by earlier Wiens and Rayleigh-Jeans. So Max Planck put forward the idea that radiation emitted or absorbed by a black body is always equal to an integral number of h nu. That is basically lambda is, that is basically the energy emitted by or absorbed by a black body, epsilon, that is equal to n h nu. So n is having a integer numbers, n is equal to 1, 2, 3 and so on. So energy absorbed or emitted by a black body is always would be a integral multiple of h nu. So according to this hypothesis, the Planck's derived a formula in terms of the energy density, and that is given by this relation. I lambda is equal to 2IHC square divided by lambda to the power 5, 1 divided by e to the power hc by lambda kt minus 1. and this formula derived by Max Planck that agreed well with the experimental findings both in the shorter wavelength region as well as in the longer wavelength region. So from this first problem, it was a beginning of the quantum physics. But according to the classical physics, it was assumed that energy was having a continuous distribution. But Max Planck contradicted this phenomena and told us that energy distributed in this black body radiation is having a discrete nature. So this was the difference from the earlier classical assumptions. So on the basis of this relation, basically he derived this energy density radiation which lies between the wavelength region lambda and lambda plus d lambda, lambda and lambda plus d lambda. So in this range, the energy density was calculated by Max Planck, and its relation was 8 pi hc upon lambda to the power 5, 1 upon e to the power sc by lambda kt minus 1. Now in case of shorter wavelength, suppose the value of lambda is quite large. So in that case, this quantity hc by lambda kt, that will become large. It will become large when this lambda is small, when this lambda is small. So when this lambda is small, so this quantity will become quite large. So its exponential will again become quite large, and we can then neglect this minus 1 here. So this formula will finally be changed to in this form, and that is the energy density for emission radiated by the black body in case of Wien's law. So Wien's law basically derived this relation on basis of his displacement law. That was a classical law. Okay. Now, similarly, we can also derive the Rayleigh-Jeans law according on the basis of this Max Planck's law. For that case, we have to consider the wavelength in the longer wavelength regions. So, if value of lambda is quite large, in that case, hc by lambda upon kt, that will become small. So when that is small, so in that case we cannot neglect this minus 1 in the expression. In fact, we have to then expand this exponential series. So after expanding this exponential series, finally we will get this result. So after expanding this exponential, this minus 1 will cancel with plus 1, and we will get the energy density that is equal to 8 pi kt upon lambda to the power 4 d lambda, which I have already told you that this is the Rayleigh-Jeans law for the black body radiation. Okay. So this was basically a beginning of the quantum physics. This was the first problem from which a deviation was created from the classical physics. There were other problems also in which classical physics was not having any explanation. For example, there was a problem of a photoelectric effect, the radiation emitted by any body after absorbing the photons. The photoelectrons were liberated, and the energy of the liberated photoelectrons was depending upon the frequency of the incident radiation. It was not depending upon the kinetic energy. So this problem was solved by Einstein, again on using this same quantum hypothesis. Then there was a Compton effect problem, in which also we were not having any explanation of classical physics, and it was explained on the basis of quantum physics. There are some other problems also. For example, there was a problem of the fine structure spectra of the hydrogen and helium atom. So how we were getting that kind of a spectra? In that also the classical physics was not giving any correct answer, and that problem was also explained on the basis of quantum physics. Now, on the basis of Planck's theory, a very important and remarkable discovery was made by the de Broglie. So on the basis, and basically de Broglie told us that the wavelength associated with any moving particle is given by lambda is equal to h upon mv. And this de Broglie's relation is valid not only for the quantum mechanical particles, very small particle, but it is also valid for the classical particles. So what is wave particle duality? On the basis of Planck's theory of thermal radiation, Einstein's explanation of photoelectric effect emission and absorption of radiation by substance, black body, radiation, etc. undoubtedly established that electromagnetic radiation consists of discrete individual particles of energy. So by this Planck's discovery, it was quite obvious that the radiation emitted by a black body is having a particle-like nature. But earlier, in case of light waves, we have already established these facts that the light waves show a wave nature for the phenomena of interference and diffraction. So we can say that the electromagnetic radiation is having a dual nature. In some case, it behaves as a particle, but when the electromagnetic radiation propagates in a medium, then it propagates as a wave. So this is known as the concept of the wave particle duality. So therefore, we conclude that the electromagnetic radiation has a dual character. In certain situation, it exhibits the wave properties, and in certain situation, it exhibits a wave properties. Now, de Broglie's matter wave concept. So as I told you that the wavelength associated by a moving particle is given by lambda is equal to h upon mv. Lambda is equal to h upon mv. So his theory was basically based on the following facts. The entire universe consists of matter and energy only. The entire universe consists of matter and energy only. Matter and energy can be transformed into each other. According to de Broglie hypothesis, the moving particle is surrounded by a wave. The wavelength of that wave depends upon the mass of that particle and its velocity. And relation, I have already told you that lambda is equal to h upon mv. So the wavelength associated with the moving particle is given by this relation. Now, as far as the derivation of this de Broglie's relation, we can use this very basic concept that energy of photon is equal to E is equal to h nu, or E is equal to hc by lambda. And by joining this concept with the Einstein's relation, that is by E is equal to taking h nu, that is hc by lambda, and then taking E is equal to mc square. And by joining these two concepts, by comparing these two equations, this is equation number 2, what we will get? We will get mc square is equal to hc upon lambda. So c will get cancelled and we will get lambda is equal to h divided by mc. That is in the case of electromagnetic radiation. So this relation is not only valid for electromagnetic radiation, but it is valid for each and every kind of a particle. So we can replace this c by v also here. We can replace this c by v also, and then this will be generalized as h is equal to mv. This is the de Broglie's relation. So this was the derivation part for this de Broglie's relation. So we have derived here this here. In terms of momentum, its value will be lambda is equal to h by p. Now, as I have told you that lambda is equal to h upon p, and the relation that is equal to h upon mv, and mv is equal to linear momentum. Now, the relation between the kinetic energy and momentum, if kinetic energy is denoted by E, then E is equal to half mv square, or E can be written as p square divided by 2m. This is the value of E. So value of P will become square root of 2m into E. So by substituting this value of P here in this relation, we can find the value of lambda, that is lambda is equal to h divided by square root of 2me. So in this expression, basically we have written this wavelength in terms of the kinetic energy of a moving particle or a moving system. Now, in terms of temperature, when a material particle is in thermal equilibrium at a temperature T, then its total energy or kinetic energy can be written as E is equal to 3 by 2 kT. So in that case, in the previously derived relation that lambda was equal to h upon 2 mv, here this E will be changed by 3 by 2 kT. E will be changed by 3 by 2 kT. So in this case, the relation will be lambda is equal to h divided by square root of under root of 3 mkt. Now suppose if a particle is moving with very high velocity and if its velocity is in comparison to the velocity of light, then what will be the relation for the wavelength lambda according to de Broglie? For that case, the mass of the particle is not going to remain constant. It is going to change according to the theory of relativity concept. And mass will vary according to this relation, m is equal to m naught divided by 1 minus v square by c square. So this relation is only valid when v is quite near to the velocity of light, when v is approaching c, though v is still less than c, but it is quite near to the value of c. In that case, the mass of the system is going to increase, and that increased mass or the variable mass is given by m, and m naught is the original or initial mass of the system. So m will be equal to m is equal to m naught divided by square root of 1 minus v square by c square. So in this basic relation of lambda is equal to h by mv, we are going to change m by this relation. So lambda will be h multiplied by square root of 1 minus v square by c square divided by m naught v, where m naught is the initial mass or the rest mass of the system. Now, de Broglie's wavelength for the electron we can find out easily on the basis of this relation. For a non-relativistic case, when the speed of electron is quite less in comparison to the speed of light, and if the parameters are known to us, we know the initial mass or the rest mass of the system, so we can easily find out the value of lambda by using this relation, where m is the rest mass of the electron which is known to us. So then lambda will be equal to this factor, that is 12.26 divided by square root of e. We have substituted the value of m and e, that is the charge of the electron. So this is the numerical which we have solved on the basis of this de Broglie's concept. Let's skip that. Okay, now let's talk about a very important aspect of the quantum physics, that is the wave function. Suppose if we are dealing a very small particles, that are electrons, protons and neutrons, as I told you, their behavior cannot be described on the basis of classical physics. For their behavior explanation, we will need a new kind of physics, and that is known as quantum physics. So for describing these quantum mechanical particles or very small particles, we need a function which is known as a wave function. Now this psi this wave function psi is basically having a two coordinates r and t in itself. Psi is a function of r and t. R is a position coordinate and t is the time coordinate. But this wave function psi is not a completely, you can say, a natural function or a real quantity function. It is a complex function. It is a complex number. So that's why it is not having a direct significance in itself, because this psi is considered to be a complex number. But when the psi is multiplied by its complex conjugate, then it gives a real quantity, and that gives us the probability of finding a particle at any particular point. So all this explanation was given by a physicist named as Max Born. So what is his concept? According to Max Born, a wave function gives the probability of finding the particle at a certain location. This is the most commonly and misunderstood concept in the quantum physics and chemistry both. It is a mistake to think of a particle spreading like a cloud according to the wave function. Only it is the probability density which we can find of the particle. So if a particle is moving in a medium, a quantum mechanical particle is moving in a medium, then according to de Broglie, we can associate a wave nature with that particle. And that wave is continuously happening phenomenon of the medium. We cannot isolate a wave. So we cannot exactly locate the particle. We can only tell us the probability of finding a particle at a particular instant at a particular position. So that was the Max Born concept. Now, as I told you, this wave function is having the two coordinates r and t, and it is a complex number in itself. Now, what is a wave function? It is having all the dynamical information about the particle. So this psi is a function of r and t. It is generally written as a psi r. e to the power minus I omega t. It is also written in this form, psi is equal to psi naught e to the power minus I omega t minus k dot r in the form of a wave also. Now, in this first mathematical form, I have taken this r, the position coordinate real, and this time coordinate as a complex quantity. But in the second form, I have taken both the position coordinate r and the time coordinate t both in the complex form. In the both way, a wave function can be written. Mathematically, it can be written in the both these form. So, but in itself, it is not having any physical significance because it is a complex quantity. Now, what is a wave function? It has all the dynamical information about the particle. More immediately, it has the information about the location of the particle. So it will tell us about the probability of the finding the particle. Now, according to the Born interpretation, the square of the wave function modulus psi square gives us psi square at a point is proportional to the probability of finding the particle at that point. So if psi is multiplied by its complex conjugate, suppose let's say that psi is written as x plus iy, or you can also write it as suppose a plus ib, then its complex conjugate can be written as a minus I by. Now the product of psi and psi star, that will be equal to a plus ib multiplied by a minus ib. A minus, that is equal to a plus ib multiplied by a minus ib. So that will give you us a real number, that is equal to a square plus b square. So now the psi star multiplied by psi, that is giving us the probability of a quantum mechanical particle at a point, and it is a real number, that is equal to a square plus b square, that is positive, then that is a real number. Now let's continue with this Born interpretation further. A wave function is in general a complex number, which I have already told you. But the psi square is always real and non-negative, which gives us the probability of finding a particle at a point. Suppose we are interested in finding a particle in a very small interval, that is dx, very small interval dx, which lies between the region x and x plus dx. So the probability will be equal to modulus of psi square into dx, and modulus is psi multiplied by psi square. So probability in a small interval is equal to modulus of psi square dx. Similarly, if we are interested in finding the particle in an entire volume, so the volume d tau can be written as dx dy dz, and the probability density will be then modulus of psi square I square multiplied by d tau. So let me clarify it, that is the modulus of psi square multiplied by d tau. So modulus of psi square was the probability of finding a particle at a point, and modulus of psi square dx was finding a particle in a small interval dx, and modulus of psi square d tau is probability of finding a particle in a small volume, which is equal to dx dy into dz. Now the total probability of finding a particle in entire space, that should be equal to 1 only. So if we integrate this function, then that should be equal to 1. And its limits can be taken from minus infinite to plus infinite. And this condition is known as the condition of normalization, which I will elaborate in the coming slides also. So this is the condition of normalization. We are free to multiply any constant factor other than 0 to psi without stopping it from the solution of Schrodinger equation, which we will discover in the coming slides. Remembering that modulus of psi square d tau or modulus of psi square dx dy dz is only proportional to the probability of finding the particle in this small volume. And if we integrate if we integrate this function, then that will give us as a total value of the probability finding in the entire volume. So this is, we have multiplied this wave function by a constant n psi, then we have normalized it, that is modulus of psi square, that is n square psi square dx. So where we have taken the space as dx, we can also write this relation for the volume d tau also. In that case, it can be written as, in that case, it would be written as n square integration modulus of psi square into d tau, that is equal to 1. So this is known as the condition of normalization. So a wave function satisfying this condition is known as a normalized wave function. So from this equation, we can also find the value of n, which can be multiplied to the wave function to write it in a normalized form, to write in the normalized form. Now, let's talk about a very important aspect of the quantum physics, which is the first mathematical equation of this quantum physics, and this equation is known as Schrödinger. Basically, it was discovered by a physicist named as Erwin Schrödinger, so that's why it is known as Schrödinger's wave equation. So, what was Schrödinger's proposal? First of all, let's try to understand that. According to Schrödinger, the wave function describing the matter waves associated with the particle satisfies a partial differential equation with the space and time as independent variables, and gives a prescription for writing down the equation for any particular system of particle. Schrödinger got this wave equation for describing atomic processes by pure thought without any regard to the experimental development of the time. According to de Broglie concept of matter waves, every moving particle associated with every moving particle a wave can be associated. So Schrödinger introduced a mathematical function represented by psi, which is a variable quantity and associated with the moving particle, and it is known as the wave function. So this Schrödinger equation mathematical form is having basically two forms. The first one is known as the time independent Schrödinger equation, and the other one is known as time dependent Schrödinger equation. So first of all, let's talk about the time independent Schrödinger equation, which doesn't depend upon the time. So in many cases, forces acting upon a particle or a potential energy does not depend upon the time, but vary with the position of the particle. The differential equation describing this situation is termed as the time independent Schrödinger equation. According to classical wave equation, or that a wave equation can be written in this form, that is d square psi over dx square plus d square psi over dy square plus d square psi over dz square is equal to 1 upon c square d square psi over dt square in the partial form. So this is the classical equation of a wave. So any function, if that is going to describe a wave, then it should always satisfy this mathematical relation. So if the psi is changed by a function, wave function, if we are describing a quantum mechanical system, then this equation can be written as d square psi dx square plus d square psi dy square plus d square psi dz square is equal to 1 upon v square d square psi upon dt square, where v is the velocity of the moving particle. Now, as I told you, this psi is a function of a position coordinate rnt. Psi is a function of So as I've told you earlier, that this psi is basically a function of r and t. R is a position coordinate, t is the time coordinate. So this is the general form. We can specify it in the form of three-dimensional coordinate, there x, y, z, x, y, z and t. So this wave function we have written as psi x, y, z, and then we have taken another function. So we have here separated the variables in the form of position coordinate, that was psi r, which has been now changed in the form of x, y, z, and other is the function ft. Now the time varying function is changing, is taken in the form of the complex quantity, that is e raised to the power I omega t. So basically we are having psi that is equal psi, which is a function of x, y, z and t, that is equal to psi function of x, y, z multiplied by other function of time, that is a complex quantity, that is e raised to the power I omega t. So this psi is here representing a real function, and this e raised to the power I omega t is a complex function. So if we are going to multiply both of them, then this entire function will become a complex quantity. So I have already told you earlier that this wave function is a complex quantity and it is not having any physical significance directly. But if we multiply psi with its complex conjugate, then only it gives a probability at a point. Okay, now psi is a function of x, y, z, t and e raised to the power I omega t. If we will differentiate this psi with respect to partially twice with respect to x, so what we have done here, we have taken this y and z to be constant, and we are only assuming that x and t are changing. So we are in the first case, if we are describing the motion only along the x-axis, so we have nullified the y and z. So wave function will depend upon x and t. Now on differentiating this psi twice with respect to x, what we will get? We will get d square psi over dx square is equal to d square psi over dx square into e to the power I omega t. Similarly, we can differentiate this in the forms of y and z also. We will get these three relations in the form of equation number 4, 5 and 6. So now differentiating this basic equation in the terms of time, that means d square psi over dt square. Now we have taken this x, y, z to be constant, and we are now assuming that time is going to change. So in that case, this function will be d square psi over dt square is equal to minus omega square psi e raised to the power I omega t. Now substituting all these values from equation number 7, equation number 5 and 6 in our fundamental equation, that was the fundamental equation of the wave. So basically we will get this relation, that is d square psi dx square plus d square psi over dy square plus d square psi over dz square is equal to minus omega square v square upon d square psi over dt square. Now this the whole relation has been changed by this del, that is del square is equal to d square upon dx square plus d square upon dy square plus d square upon dz square plus multiplied by psi plus omega square v square psi is equal to 0, where this is the value of del square as I have told you. Now the value of omega is equal to 2 pi nu by lambda, and v is equal to, so by dividing this omega by v, that is omega square upon v square, we will get 2 pi nu upon h square. So how we have find the value of this omega upon v, that thing we can see. Basically what we are getting here, omega square upon v square, where v is the velocity of the moving particle or a moving wave. So basically we are interested here in finding the value of omega upon v. Now omega is equal to 2 pi nu, where nu is the frequency, omega is the angular frequency, and the value of v is equal to nu into lambda. So nu will cancel. So value of omega upon v is equal to 2 pi by lambda. So this value is used in these equations, 2 pi by nu upon lambda, that is the value of omega upon p. Now here basically the value of lambda is equal to h by p. We know according to de Broglie relation, lambda is equal to h by p, and we have earlier stated the value of p was square under root of 2m into e minus v, that is 2m into e minus v. So we can take here the value of omega square upon v square is equal to 8 pi m e minus v by h square, that is equal to 2m multiplied by e minus v into h cross square. Now substituting these values of omega square upon v square in equation 9, what we will get? We will get the Schrodinger's time independent equation, that is d square psi plus 2m e minus v into psi h cross square is equal to 0. Now for deriving the Schrodinger's time dependent equation, now we have to take a different approach, that is we have to first write this psi as a function. Psi is equal to psi naught e to the power minus I omega t, exponential with a minus sign, and then we have to differentiate this psi. So d psi upon dt is equal to psi naught minus I omega e raised to the power minus I omega t. Now value of omega I have already told, that is equal to 2 pi nu e to the power minus I omega t. The value of d psi upon dt is equal to minus 2 pi nu into psi. So the value of d psi upon dt is equal to minus 2 pi I nu into psi. Now this nu should be changed in the form of energy. Here, so d psi upon dt is equal to minus 2 pi I, and nu has been changed E divided by H, because all of us knows that E is equal to H nu. So this nu has been changed here. So value of d psi upon dt is equal to, value of d psi upon dt is equal to minus I, value of d psi upon dt is equal to minus I E over H cross into psi. So this can be, if we take this E from in this relation, minus I and H in left hand side, so we can write that. So we can write this. We can write this E psi is equal to I H cross d psi over dt. Or substituting the values, we will get this basic equation in this form, that is minus H cross square by 2m del square psi plus V psi is equal to I H cross d psi over dt. And this is known as Schrodinger's time dependent wave equation. So by this simple mathematical manipulation, we can write both these equations, Schrodinger's time dependent and independent wave equation. Thank you to all of you.